two thin metallic spherical shells of radius R1 and R2, R1 less than R2. You can see R1 is inner radius and R2 is outer radius, are placed with the centers coinciding. The inner shell is maintained at temperature θ1 and outer shell is maintained at temperature θ2, where θ2 is greater, and means outside temperature is higher, so heat will flow inside. Okay. Now, the rate at which heat flows readily through the material is, so we have to find dq by dt. And for dq by dt, logic is to find dt by L by Ka, dx by Ka. Now, we have already solved so many questions over linear rods, but in this case, how to solve dx by K, let's see. So here, we'll take a very small elemental sphere of hollow sphere of very less thickness, and that thickness will be taken as dx. Okay. Now, the heat is coming like this, okay, from outside, and we always take that area which is perpendicular to the heat flow. So that area is the area of the sphere. So dx, as we have taken the length of the rod, just like heat flows, and we take this length as along the flow of the heat. Similarly, when the heat flows like this thickness is the length along the flow of the heat. That's why this part is taken as dx. Then simple logic that what we are using for pi dx and L by L, this is Ka. Area is taken as sphere. Okay. So K is thermal conductivity and area is as it is, as we know the formula for spherical bodies, 4 pi x square. So our thermal will be, now integrating, 1 upon 4 pi k, which is a constant, can be taken out. 1 by x square dx 1 by 4 pi k minus 1 by x R1 to R2. That is what we are required. So when we solve, we get this. This is after solving the thermal resistance. Now we can put it into this formula. So we get θ2 minus θ1, which is the dt, divide by this entire thing. On rearranging, we get 4 pi k R1 R2 θ1 minus θ2. Sorry, θ2 minus θ1, because outer temperature is higher, upon R2 minus R1. It's better to remember this formula, because in exam, if MCQ comes, you are not expected to derive all this and waste your time. Okay, so please remember this: 4 pi k R1 R2 θ2 minus θ1 R2 minus R1. Please remember one thing: 99.9% times the inner temperature is higher because furnace is inside. So just check this. Okay, θ1 minus θ2 accordingly, because we always give the answer flow rate as positive.